picking up good vibrations.
We'll now talk about a very, very important property of the Fourier transform, the convolution property. To explain this property, let me start by providing some motivation. Now, we have seen that if the input to an LTI system is a complex exponential, then the output is also a complex exponential multiplied by a complex number. If the input is a cosine or a sine, that same complex number that multiplies the complex exponential, we have to extract the magnitude and the phase, and the output will be a cosine multiplied by that amplitude and by that phase. Now, analyzing carefully this complex number, we see that it's nothing more than the Fourier transform of the impulse response of the system evaluated at the frequency of the impulse signal, the complex exponential or the cosine or the sine. Now, if the input is a sum of complex exponentials with different frequencies, the output will also be the sum of complex exponentials with exact the same frequencies, and each of these complex exponentials will be multiplied by a complex number, which is again the Fourier transform of the impulse response of the system evaluated at the corresponding frequency of these complex exponentials. Now, we managed to write an arbitrary aperiodic signal as a sum or an integral of elementary complex exponentials, so we should expect a similar property in this setting. In particular, we should expect to see a product between the Fourier transform of the impulse signal and some complex numbers related to the Fourier transform of the impulse response of the system. And this is in fact the case. The property goes as follows. If x of t is the input of the LTI system and h of t is the impulse response of the LTI system, and if we consider their Fourier transforms capital X of j omega and capital H of j omega, then the Fourier transform of the output is the product between capital X of j omega and capital H of j omega. So a convolution in time is nothing more than a product in frequency. A convolution between X and H corresponds to a Fourier transform that is capital X j omega times capital X of capital H of j omega. Now, we have talked about this in the context of convolution where we have a signal entering an LTI system and a signal out and an impulse response, but this property is a mathematical property that holds for any convolution. So I have two arbitrary signals, X and H. If you want to compute the Fourier transform of the convolution between X and H, that is nothing more than the product of the Fourier transforms of X and H. This result is very important and has many applications discussed, a few of those discussed now. The first is that this property allows us to circumvent convolution. Instead of computing convolution in time, we can follow the following procedure. We can first compute the Fourier transform of the input signal x of t, leading to capital X of j omega. Second, we compute the Fourier transform of the impulse response h of t of the LTI system, and that we denote by capital H of j omega. Third, we multiply the two, and that leads to the Fourier transform of the output, denoted by capital Y of j omega, which is equal to capital H of j omega times capital X of j omega. Finally, fourth, we have to take the inverse transform of y, capital Y of j omega, and we obtain y of t. Let us see how this works through an example. Suppose that we want to compute the output response of an LTI system with impulse response e to the power of minus t when t is positive and 0 when t is negative. So it's a causal system. And the input signal is, again, a one-sided exponential, which for positive time is equal to e to the power of minus 2 times t, and is 0 for negative time. So we can follow the procedure. We can take the Fourier transform of the impulse signal and the Fourier transform of the impulse response. And we have seen already formulas for that. We get respectively 1 over j omega plus 1 for the impulse response of the system, and 1 over j omega plus 2 for the input. Now, step number 3, we multiply the two. And for convenience, so we get 1 over j omega plus 1 times 1 over j omega plus 2. And for convenience, I'm going to split up this using partial fraction decomposition. And so we obtain 1 over j omega plus 1 minus 1 over j omega plus 2. Now, again, using the Fourier transform pairs, we know what are the corresponding time domain signals for each of these Fourier transform. So for 1 over j omega plus 1 is simply e to the power of minus t for positive time and 0 for negative time. And for 1 over j omega plus 2 is e to the power of minus 2t for positive time and 0 for negative time. And that means that if you have a weighted sum of Fourier transforms, that corresponds to a weighted sum of signals. And so the inverse Fourier transform of 1 over j omega plus 1 minus 1 over j omega plus 2 is nothing more than the signal depicted here, e to the power of minus t minus e to the power of minus 2t for positive time and 0 for negative time. Now, another application is filtering. Consider an impulse signal with a Fourier transform as the one depicted here. And this Fourier transform has a significant content in low frequencies and then also in high frequencies. Now, this signal can represent, let's say, my voice with some echo or my voice with some disturbing sound like a cat meow. My voice corresponds to the low frequency content, and the echo or the cat meow corresponds to the high frequency content. Now, why do I say high frequency content? Is a signal with a high frequency pitch that varies faster than my voice signal. And that's why it is a higher frequency signal. Now, suppose that we want to remove the echo of the signal. Now, if we multiply the Fourier transform of my voice plus the echo, or my voice plus the cat meow, with a filter that has the Fourier transform as the one depicted here in blue, then once we multiply the two, we remove the components that correspond to the noise in the signal, the cat meow or the echo. So we have to find a system whose Fourier transform is capital H j omega depicted here in blue. And if we can find that, if we convolute that, if we take the convolution between the input signal and if we put it in the system, the result of the convolution will be the product of the Fourier transform of the impulse signal and the product of the Fourier transform of the impulse response, and this will lead to the blue output seen here. Now, in turn, let's say that we want to remove my voice and keep the cat meow signal. So we should design a system with an impulse response that has the Fourier transform depicted here in red. Once we multiply the two, this will lead to a Fourier transform of the output that corresponds exactly to the Fourier transform of only the cat meow. We are left with the question of how to design systems in continuous time with impulse responses that have these blue and red Fourier transforms capital H of j omega. Now, we will not address this here in continuous time, since we will address that later in discrete time where this is trivial.